Hi everyone, welcome back. In this video, I'd like to feature a custom build that I did a few weeks ago, and it's horn number 1689, and it's a solid walnut circular horn using an 800 hertz low frequency cutoff. And so in this video, I'm just going to show some test data between 3 different compression drivers, and just to have an overall discussion about where this type of horn could be used in a complete system. So now, I do offer the 3D CAD files available. If you click on the link on my blog, I'll post a link in the description as well. You can download the 3D CAD files, and this allows the DIY enthusiast to either CNC machine the horn themselves or have them 3D printed. And so it just helps if you're really into the DIY. Here you can see here that it's shown as a step file. And yeah, so looking at the overall design of this particular horn, I used a T-slot cutter mounted in my CNC machine to produce this undercut, and this actually is I'm able to mount the driver in a really elegant way so that it doesn't have any separate pieces or adapters to mount the driver. And so the stud there that comes with the compression driver, typically it's a M6 by 20 millimeters long stud, and so this just facilitates that. And then you just put the nut on there, and I haven't showed it in my CAD model, but you get the idea. Now the overall horn flare geometry uses my ES horn flare curvature, and it has the complete wraparound, and then it's actually recessed out on the back side of the horn. So now, going to the actual test data, I started out with the RCF ND350, and so you can see here the resulting frequency response. Now, when you're dealing with horns, the mouth of the horn, if the mouth area is too small, what you end up with is what's called first order reflections as a result of the abrupt change at the mouth of the horn. And so what I've tried to do here is create a very wide flare rate with a very large mouth area. And so the goal here is that first of all, you have virtually no first order reflections at the low frequency cutoff of the horn. And so if the mouth of the horn was too small, you'd start to see frequency response peaks and valleys near the cutoff of the horn. And so you can see clearly that the horn is completely absent of any of that, which indicates that the horn is free of any of those first order reflections. And that is probably what people find most objectionable with horns, is that there's reflections occurring in the horn. And so the goal here is to create a horn that's completely void of any reflections whatsoever. And so you can see that the response is relatively smooth. It does have a falling response. Now, if we look at the off-axis polar map, you can see that the horn is very consistent in the off-axis. It has a gradual narrowing of the directivity. And so you can see here I have added an overlay showing where the -6 dB down point is in the graph. So if you follow it to 10 kilohertz, you can see that we're at about 35 degrees off axis, so about a 70-degree listening window at 10 kilohertz. And so it's not the widest coverage, but we are getting pattern control down to about 600 hertz. And so this is significant in that when you're doing your crossover design, you're actually able to pair this horn with a woofer that's quite large. So for example, you can go up to probably a 12-inch woofer with this particular design. And so what's going to happen is that when you do your crossover point at, say, for example, 800 hertz, you're going to have a really good matchup in the off-axis polar with this particular horn. If I had tried to make the mouth smaller, we would see issues, like I mentioned earlier, in the frequency response. But in addition to that, we would actually have less pattern control in the 800 hertz region. You'd actually see this red start to go right over into the 90 degrees off axis. So we would have an inconsistency in the matchup at the crossover point when if we were to go with a smaller mouth horn. So just something from a general design perspective that what we're trying to achieve here. I've shown the off-axis in a different way, which is just the kind of a waterfall type display in the Arta software. Also, there's another way of showing it again. I think this is called Waterfall 2 in Arta software, and it just kind of highlights how consistent the off-axis is, which indicates that the horn is free of any edge diffraction or resonances. So I've really gone to really great lengths to minimize any chance of this horn having any kind of coloration to the sound. So burst decay, we're seeing a very clean burst decay on the RCF compression driver. At 10 kilohertz, there is a mild resonance, but this is pretty typical for compression drivers of this type. And I've started to show cumulative spectral decay as well. Now, here you can see this is likely the mechanical resonance of the driver, which in the published data for RCF, it is just below 1 kilohertz. But the nice thing about the RCF is it does have bandwidth from about 1 kilohertz up to where the main breakup mode is on this, which is around 15 kilohertz. So step response is free of any kind of abrupt issues. You can see that it has a very fast rise in decay. Looking at distortion on the driver, this is very typical. This is a 12-band multi-tone at 90 dB, and then the test signal starts at 1 kilohertz up to 20 kilohertz. So distortion, you can see here, rises a little bit, which we'll see later that it's pretty consistent with the other brands of compression drivers. I did want to point out too, though, the VioWave SRT7 at the same test SPL, I have it here. Now I am using a high pass on this with it's a 4 kilohertz high pass, but it does highlight the superiority of the pure ribbon from VioWave when it comes to distortion. It's a full 75 dB down on the distortion. So just a side note there, that there are other driver formats that do quite a bit better than the compression drivers. Now I will mention too that a dome tweeter will do worse than this compression driver. So in order of superiority, we would go dome tweeter, compression driver, and then the best that I've been able to measure is the VioWave pure ribbon tweeter. So now I decided to implement a passive crossover on the RCF compression driver. Now I did a high pass first order, and then I did a contour circuit, and so I believe I did an overlay. So here you can see the blue is the raw response of the compression driver, and then the contour circuit that you can see here, which is comprised of a 10 ohm resistor and a 1.5 microfarad capacitor. And so what that actually is doing is it's contouring the response across its bandwidth, and it's allowing the high frequencies to at the 15 kilohertz region to kind of maintain the same level. However, through the mid part of the compression driver, we're bringing it down around 7 dB. And so we're flattening the response of the driver. And so what that's going to do is bring up more upper treble detail out of the compression driver. And this is certainly worthwhile doing. It's going to balance out the overall sound and make it sound a little more hi-fi. And so the next test, I tested the SB Audience Rosso 45 CDN PK. So I believe the PK means that it has, actually, I don't know for sure. I'd have to look that up. But so you can see here the response of this. Now, this has a flat response in the sense that the lower treble is consistent with the upper treble. And so we do see the breakup starting to occur at around 14, 15 kilohertz. Burst decay, we can see that it's not as clean as RCF. We do have some resonances in the 6 and 8 kilohertz region, and then things get pretty bad at the breakup, which is to be expected. And then the waterfall decay, you can see that there pretty strong representations there. So nothing really noteworthy on the step response. Now doing the exact same intermodulation distortion on the SB audience driver, you can see it's pretty clean through the lower part of the treble, and then it gets pretty aggressive with the distortion in the 5 and then the 10K. So these do correlate with what we're seeing consistently in the time domain measurements. We can see these showing up as intermodulation distortion as well. So the next driver that I tested was the Fatale Pro HF108R. And so you can see the response here. It's actually quite good in the sense that it's quite flat until its breakup, which happens a little earlier at around 13, 14 kilohertz. But it is showing a very flat response. And then the burst decay is showing a very clean result until you get to the breakup. And then the waterfall again is showing a pretty clean result as well. Now it does have something happening in the 12 kilohertz region. You can see it there. So probably this little dip there is what we're seeing in the time domain. Step response, nothing of note there. However, if we look at the intermodulation distortion, we can see the noise profile there. The sideband profile is quite a bit flatter than what we were seeing with the SB audience. And so I decided to use the same passive crossover on this driver as well that I did with the RCF. And you can see the response here is pretty linear, and then it gets a little bit ragged past 10 kilohertz. And so I'm just doing an overlay with the passive crossover showing against the raw response of the driver. So now I did subjective listening on these, and I found that the RCF and the Fatale driver produced very refined, detailed sound quality, and the SB audience trailed closely behind the RCF and the Fatale. If I had to pick between the RCF and the Fatale, I would pick the RCF. Subjectively, I found that it had a really rich and full vocal, in the vocal region, it had a very rich sound. And so with the horn, I was able to hear every little subtle nuance in the soundtrack, making for a very enjoyable listen. So that pretty much concludes this. Now, like I mentioned, I have the 3D CAD files, and also there's a product link there as well if you're interested in purchasing these horns custom made. So the customer in this particular instance was using the Radian 1-inch compression driver with the beryllium diaphragm, and he had sent the horns to Danny at GR Research for system integration with crossovers. So we'll see how that works out for him. So that's it. Take care and have a great day.